Okay, I was asked about problems 19 and 17 on 6.3, so I thought I would go over those first right now. And that's more relevant to you for the exam, obviously, than if I do the next section. So I think we're going to be good. Okay. All right, so let me get back here. Okay, so again, I'm actually a little bit ahead. Okay, I was supposed to do 6.5. I'm already done with 6.5, so I'm on to 7.1. Okay, I'm not going to stop. You know, I might fall behind later, or I might get sick. So, you know, if I'm ahead, it's nice to stay ahead. Okay, and yeah, so you say, what do I turn in for the homework? Here it is, right? So turn this in Tuesday. Okay,
so real quick,
17. Okay,
sorry, real quick, homework.
Go ahead.
7.1 isn't due, correct?
7.1 is not due, correct. So 7.1 through 7.8 is on test 2. So you turn that in on what? Thursday, October 1st, for now, unless things change, right? So yeah, I'm starting lecturing on 7.1, but that's not due. You just turn in, it's a chapter 6 exam. The next test is a chapter 7 exam. So even if I sneak in some new stuff again, you only are responsible for this. So yeah, I'm gonna do some 7.1 today. Just take notes, but don't study it for the test. Okay, 6.3 was on the shell method. Okay, y equals 4x minus x squared, and y equals 3, and you're spinning it about x equals 1. Okay, now, you should know this is a parabola which opens down because there's a minus sign. Okay, now how do you know what to integrate from? Well, let's set these two equal to each other. You know y equals 3 is a horizontal line. Okay, so it's a horizontal line, and there's going to be something like that because I know it opens down. So where do they touch? We set them equal, right? So where the two graphs intersect, find out where they touch, set them equal. So 4x minus x squared equals 3. Move these two guys over. So add x squared, subtract 4x. It'll look like that. Factor into x minus 1, x minus 3 equals 0. And that gives me x is equal to 1 and 3. Okay, so they touch at 1, 3, and 3, 3. I already know that y equals 3. Okay, 1, 3, and 3, 3. Just for fun, I plugged in 2 just to see what would happen. So if I plug in 2, 2 here, and 2 here, 4 times 2 is 8. 2 squared is 4. So 8 minus 4 is 4. So this is a 0.24. So that clinches it. I know that it looks like so. All right, so I'm taking this region and I'm spinning it about the line x equals 1, which is right here. So I'm taking this thing and spinning it over here. Okay, so this is the height. So I'm doing my cross sections as delta x. So I'm integrating with respect to x. This is the height. The height is the difference between the top and the bottom. So the top is 4x minus x squared, and the bottom is y equals 3. So the height is 4x minus x squared minus 3. Okay. And the radius is here, the distance from here to here. How do I figure that out? Well, the distance from here to the y-axis is what we normally call x, right? So always think back to this basic picture where you first learned the xy coordinate system, right? If I have a point xy, x is this distance, and y is this distance. So the distance from here to here is x. The distance from any point to here would be y. Okay. Now this is 1. So the difference between them is x minus 1. So my radius is x minus 1. Okay, so I'm going to be integrating 2 pi rh. R is x minus 1. H is this guy, 4x minus x squared minus 3. Right, so again, that's why I don't want you to think in terms of integrating 2 pi xy. In the easiest case scenarios, yes, it was 2 pi xy, but this is an easiest case scenario. All right, so that's essentially it. Take out the 2 pi, multiply all that mess out. So you take x times that, negative 1 times that. So it comes out to be 4x squared minus x cubed minus 3x. That's x times that, and that. And then negative 1 times that, and that. You just change every sign. So minus 4x plus x squared plus 3. And combine like terms, negative x cubed is all by itself. X squared are right here. So 5x squared. Okay, and the x's, negative 3x and a minus 4x is a negative 7x. If you haven't already done so, could you please mute yourselves? I'm hearing some background noise. So everybody please mute. Thank you. And 3 is just 3. There's no other constant. Okay. So there we go. So integrate, 2 pi is outside, negative x to the 4th over 4, plus 5x cubed over 3, minus 7x squared over 2, plus 3x, from 1 to 3. Integration was 1 to 3. Notice they didn't give us the 1 to 3. We had to figure it out. How do we figure out? We set that equal to that. And that told me, okay, now we're integrating from 1 to 3, because we didn't know that ahead of time, right? Okay, this set of parentheses, plug in 3. This set of parentheses, plug in 1. Okay, so plug in 3, negative 81 over 4. Plug in 3. 3 cubed is 27. 27 times 5 is 135. Plug in 3. 3 squared is 9. 9 times 7 is 63. 3 times 3 is 9. Plug in 1. 1 raised to anything is 1, right? So it's negative 1/4 plus 5 over 3 minus 7 over 2 plus 3, right? If you put a 1 here, that's 1. Put a 1 there, that's 1, right? So I just have that. Okay, so I got a lot of a big mess here. What did I do over here? Okay, these 4 I left alone. These 4 I changed the sign because it's minus parentheses, right? So if it's minus parentheses, you change all of these signs. So 1, 2, 3, 4 stays the same as 1, 2, 3, 4. But these 4 change signs. So plus, minus, plus, minus. Okay, and then what am I trying to show here? These 2 have a common denominator of 4. So it's negative 81 plus 1, which is negative 80. Negative 80 over 4. Negative 20. These 2 combine to be 130 over 3. These 2, negative 63 plus 7, negative 56 over 2, which is a negative 28. And 9 minus 3 is 6. Okay. This is just arithmetic, really. Okay, I leave the 130 over 3 alone because I don't like it. So negative 20 minus 28, that's a negative 48, plus 6 is a minus 42. Finally, I get a common denominator. So 42 over 1 is 126 over 3. So this comes out to be 4/3 times 2 pi. Final answer is 8 pi over 3. Okay. So that's 17.
Hey, Professor, that one's different too there. This is Rashawn.
This one's different? I don't think so. I think this one was off the book. Number 17, is that what you mean? Okay, I think
23, right?
6.317?
Oh, I'm sorry. No.
Yeah. I think
That's right.
Okay. But yeah, feel free to point me out. I've messed up already several times. Okay, 19. X equals 2y squared for y is greater than or equal to 0 and x equals 2. Okay, x equals 2y squared looks like that. Y is greater than or equal to 0 and x equals 2. And you're spinning it way up here about y equals 2. So if we're doing shell method, your slices are going to be this way, delta y. Okay, so this is the point 2, 1. Okay. X equals 2 is right here. X equals 2. If I plug in 2, that means y is 1. Okay, slice like so. All right, so if I'm spinning it way up here, this is my radius. How do I find the radius? The distance from here to here is 2. The distance from here to here is y. Therefore, this is r minus 2y. So that's the radius. And this is the height. It's upper minus lower. The upper is 2. The lower is, well, x. But in this particular case, x is 2y squared. So the height is 2 minus x, or 2 minus 2y squared. So that's going to be my height. So my radius is 2 minus y. The height is 2 minus 2y squared. So I'm good to go. So I'm integrating with respect to y. My slices are delta y. So I'm integrating from 0 to 1 2 pi RH, radius times the height. Okay, so that's 2 minus 2y squared times 2 minus y dy. Okay, take out the 2 pi, just FOIL this out. So 4 minus 2y minus 4y squared plus 2y cubed dy. All right, integral of 4y. Integral of negative 2y, negative 2y squared over 2, that's the same as negative y squared. Integral of this is negative 4y cubed over 3. Integral of this is 2y to the 4th over 4. 2y to the 4th over 4 is y to the 4th over 2. 2 pi, paren, 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 paren. Plug in 0, you get all zeros, which is nice. Plug in 1, 4 minus 1 minus 4/3 plus a half. Okay, it's nice to plug in 1 because 1 raised to anything is 1. Okay, so 4 minus 1 is 3. Leave that alone, leave that alone. And now my common denominator is 6, right? So 3 is 18 over 6. Negative 4/3 is negative 8 over 6. 1/2 is 3 over 6. Cancel the 2 with the 6, giving me a 3 in the bottom. That comes out to be 13. Final answer is 13 pi over 3. And that's about it for that one. Okay, so I put that away. All right, so now I'm going to go back and do 7.1. Yes, the problem that I did last time was bogus, but at least you learned something. Okay, so 7.1 is on integration by parts. Go ahead and take notes, but don't study it for next Tuesday's test. Wait until after the test to start studying it, right? But I can't just stop, so I've got to keep going. That's the nature when you have a class that just meets twice a week for 2.5 hours, right? So I have to keep going. All right, so 7.1, integration by parts. Once again. Okay, the formula that you want is this. Put it on your cheat sheet. Integral of u dv equals uv minus the integral of v du. Okay, so even though the problem that I did last time wasn't on a book, but the process is correct. So it's a good introductory problem, I suppose. So you have an integral that maybe you can't evaluate. The whole idea is to change it so that you have a u, a v, a du, and a dv. Plug it into this, and hopefully the second integral is better than the first integral. Okay, so that's the idea behind integration by parts. All right, by way of introduction today, I thought I'd start off by saying, what is the integral of the natural log of x dx? Okay, so at the end of class last time, I said we prefer not to integrate ln x. We prefer to differentiate ln x. Right, so if you have an ln x within an integration problem, you would prefer to differentiate rather than integrate. So now the question becomes, what is the integral of ln x? It's actually not that nice. Okay, so what is the integral of ln x dx? To prove it, you actually do integration by parts. So I'm going to use this formula. So I have to declare something as u and something as dv. Well, here there really isn't any choice. There's no choice. You need a u and a dv. The dv has to go with the dx, and the u has to go with the part that doesn't have the dx. So there's no choice. Let u be ln x, dv equals dx. Okay, differentiate this side, integrate this side. Okay, you might recall in the problem I did last time, right? The u side you differentiate, the dv side you integrate. Okay, so what's the derivative of ln x? 1 over x. We write it in differential form. That means du equals 1 over x dx. And pretend you put an integral here. Integral, v equals x. If dv equals dx, v equals x. This will happen a lot. I guess a weird way to think of this is take off the d on both of these, right? If I just eliminate the d, which means take off the derivative, as it were, then v equals x. All right, now I throw it into here. I have u, v, du, dv. Take those 4 parts and put it in here. So now that I have this, right, the integral is of the form u dv. If u is ln x, there's my u, and my dv equals dx, dv, then it's u dv. So that's legitimate. Okay, so here we go. u times v. U times v is x ln x. This is my uv minus the integral of v du. So v is x, du is 1 over x dx. Very conveniently, the x's cancel out. So I'm integrating 1. I like that. So did my new integral, did this integral come out easier than this one? Yes, tremendously. I'm just integrating 1. So it's integral of 1 x. So x ln x minus x plus c. Okay, so this happens to be the integral of natural log of x dx. So, do you want to memorize it? It's up to you. I mean, you're allowed to put it on your cheat sheet if you wish, but there aren't that many instances where you have to actually memorize it. As you can see, it's not a very nice answer. The derivative is nice, right? Did you remember the derivative of ln x? 1 over x. But the integral is this mess. Okay, and then just for fun, a little timeout. If this is the real answer, the derivative of this should be natural log of x. So let's try it. Okay, so let's differentiate x ln x. That's a product. So remember the product rule? Product rule says take the first function times the derivative of the second, right? So x times the derivative of ln x, which is 1 over x, plus the second function ln x times the derivative of the first, but the derivative of x is just 1. So I have ln x times 1, minus the derivative of x, which is minus 1, and the derivative of any constant is 0. Okay, so these x's cancel out. That 1 cancels that 1. So yes, indeed, I do have natural log of x. Okay, so that's the end of the proof. We have proved that this is the antiderivative of ln x because the derivative of this comes out to be natural log of x. Okay, you can memorize it or not. I don't think it's worth memorizing. And of course, right now, you get a cheat sheet anyway if you needed it, but there aren't that many cases where we need this. As you can see, it's not as nice as a derivative. The derivative of ln x is just 1 over x that you learn in Calc 1, right? Okay, so now let's do some more problems with integration parts. Okay, number 3, and I should have checked these. So these should all be matching the 8th edition. Okay, all right, x cosine 5x dx. All right, so just like over here, it seems like you have two choices. Let u be the x squared or let u be the ln x. And how do you know? So now we know that when we have an ln, we prefer to differentiate ln. So normally let u be the ln part. Okay, what happens if I have this? So again, I have two choices. I can let u be x and dv be all the rest of the stuff. Or I can let u be cosine 5x and dv be these two combined. Okay, and again, you should know multiplication is commutative. I mean, you can stick the x over here if you want. So in other words, you shouldn't have to say, oh, they're not together. There's no together, right? If you have a times b times c, you can mix them up any way that you want. Okay, let's try u equals x and dv is the rest of the stuff. Okay, so if this is u, this is dv. Now it looks like this. So u equals x, dv equals cosine 5x dx. Okay, this side you differentiate, this side you integrate, like over here. Differentiate, integrate. So if u equals x, du equals dx. Okay, that's always going to be the case. We will see this happen a lot. So if u equals x, du equals dx. It's almost like you d both sides, or you can say differentiate both sides. If you put a d, du equals dx. If you stop and think about it, it's the exact opposite of this. Here, you just lose the d, take off the d, b equals x. On this side, you just put on the d, put a d there and a d there, right? Integrate. Okay, what was the integral of the cosine? Integral of cosine is a sine, right? Careful, not the derivative. I wasn't asking for the derivative of cosine, which is negative sine. The integral of the cosine is the sine, right? Because the derivative of sine is cosine. And then by the chain rule, okay, so if I were differentiating this function, when I get to this stage, I would multiply by 5. So therefore, when I integrate, I divide by 5 or multiply by 1/5. Okay, so integrating here, the integral of dv is always v. The integral of this, pretend you have an integral, it's 1/5 sine 5x. And again, how can you always double check your answer? Well, how about differentiate? What is the derivative of 1/5 sine 5x? The derivative will be 1/5 cosine 5x times 5, which is the derivative of 5x. Well, that 5 is going to knock out that 1/5, and you got that right there. So it works. All right, so I have what I want. I have u, v, du, and dv thrown into the formula. So the integral is u times v. So that times that. The normal way to write it is first the coefficient, 1/5, then the x, and then the trig. So 1/5 x sine 5x minus, by formula, integral of v du. So minus 1/5 you can take outside the integral. You're always allowed to pass constants in and out. Okay, v 1/5 sine 5x du, which is dx. Okay, so look at what happened. I started off with x times a trig function. And what's my new integral? Just a trig function. So it got better. I lost the x, essentially. Okay, so 1/5 x sine 5x minus 1/5. What's the integral of this? So the integral of the sine is negative cosine 5x. And once again, by the chain rule, times an extra 1/5. Okay, so again, it's the reverse of the chain rule from derivatives, right? Remember, if you had to differentiate this, then when you got to the 5x, you multiply by 5, right? So since we're integrating, you do the opposite. You divide by 5 or say multiply by 1/5. Okay, and then just clean it up. That comes out to be a positive 1/25. So final answer, 1/5 x sine of 5x plus 1/25 cosine of 5x plus c. Okay. All right, now the problem's done, but I'm actually going to dig deeper. Let me show you what happens if I reversed it. Okay, I let this be u, this be dv. Suppose I let u be the cosine of 5x, and dv was x dx. Okay, so let me show you what happens there. Suppose u equals cosine 5x, dv equals x dx. Okay. So differentiate this side, integrate this side. So what's the derivative here? I forgot to write the dx, sorry. So u equals cosine 5x. du is negative 5 sine of 5x dx. Okay? So the derivative of cosine is negative sine, and then by the chain rule, I have to multiply by the derivative of 5x, which is negative 5. And decide to integrate. So v is x squared over 2. Okay, so everything's fine. Now I throw everything into the formula. So by formula, it goes u times v. So that times that. I'll write 1/2 x squared cosine 5x. There's my uv. Whoops. That. Minus the integral of v du. So v du. So to make it easier, I'll take the constants out. Negative 5/2 x squared sine 5x dx. Okay, and two negatives make a positive. That's nice. So plus 5/2 x squared sine 5x dx. Okay, and by the way, all of this is true. It's still a true statement. But let's take a look at what we had. The idea is to get a nicer integral. By doing this integration by parts, I get something nicer. Let's take a look at the original. The original had x times a trig function. I now have x squared times a trig function. So it got worse. This is worse than the original. If you can't read that, that says worse than original. Okay, I started with x times a trig function. I now have x squared trig function, so it got worse. All right, so that leads us to believe if I have a polynomial times a trig function, I want u to be the polynomial. All right, so I've got a little mini chart here. You can write it down or not, just take a look at the video later. All right, so if you're integrating a polynomial with a trig function, normally let u be the polynomial and dv is the rest. Okay, so that's sort of like the one we just did. X cosine 5x, let u be the polynomial, the rest is the dv. Okay, so polynomial times trig, u is the polynomial, dv is the rest. Same thing if you have a polynomial times an exponential, okay, like an x and e to the x. Let u be the polynomial and dv be the rest. And I'll show you an example of this right now. polynomial times an exponential. Okay, number 5 is exactly like that. Okay, integral of t e to the negative 3t dt. Okay, so it's a polynomial times an exponential. So let u be this. The only difference is that they're giving us t instead of x, but it's the same thing. And I'll share with you one little timeout. Okay, if this had been negative 3t squared, if this was negative 3t squared, I wouldn't do integration by parts. I would just do a u substitution. If this was a 3t squared, because the derivative of negative 3t squared is negative 6t, there's a t over here. So I would just do a regular substitution. Okay, but not when it's like this. All right, so polynomial times an exponential. So let u be t, dv equals e to the negative 3t dt. So that's u. All the rest of the stuff is dv. So it does look like u dv. So once I find all my parts, I plug into this. Okay, differentiate here. Yeah, whenever you see this, you just put a d on both sides. du equals dt. Integrate. Okay, so again, think in terms of the chain rule in reverse. Okay, so let me cover up the answer for a moment. You may have already seen it, but that's okay. If I ask, what's the derivative of e to the negative 3t? The derivative is e to the negative 3t times negative 3. You would multiply by negative 3 by the chain rule. All right, that's for taking the derivative. So when I integrate, anti-differentiate, I don't multiply by negative 3. I divide by negative 3, which is the same as multiplying by negative 1/3. So the v part is negative 1/3 e to the negative 3t. Right, now I have u, v, du, and dv. Throw it into here. Okay, so the integral by formula is u times v. So that times that. The way you normally write it is the coefficient, negative 1/3, then the polynomial, then the e. So negative 1/3 t e to the negative 3t. And you might say that's kind of complicated. It doesn't matter how complicated it is. I'm not doing anything to it. I'm not integrating it. I'm not differentiating it. See, look over here, uv. So it might come out bad. Doesn't matter. I'm not taking its derivative. I'm not taking its integral. I'm just leaving it. So I don't care how bad it is. Minus the integral by formula, v du. So v du, here's the v, negative 1/3 e to the negative 3t, and du is the same as dt. And simplify this, I got a double negative, negative, negative becomes positive, take out the 1/3. Okay, so did I get an easier integral? Yes, I did. I started off with t times e stuff, and now I just have e stuff. So it got better, right? I lost the t, which is what I want. Okay, and what's the integral of e to the negative 3t? We just did it. So leave that alone, leave the 1/3 alone. Integral of e to the negative 3t is negative 1/3 e to the negative 3t plus c. Here we're doing indefinite integrals again, means there's no number here and no number here. So if you have a number here and here, that's a definite integral, like most of the last chapter that we did for the test on Tuesday. But this is an indefinite integral, which means put the plus c. And let's see, what is that, negative 1/9? So final answer is negative 1/3 t e to the negative 3t minus 1/9 e to the negative 3t plus a constant. And there we go. Okay. All right. Okay. I'm going to jump way over to 25. There are some problems in between that are a little bit harder. So I'm going a little bit out of order. But I want to show you easier ones before I do the harder ones. Okay. I was going to show you 25, 33, and 37. Now 25 is a definite integral, although it doesn't change that much. And 33 is also a definite integral. Okay, it's the integral from 0 to 2 of y sinh y dy. This is hyperbolic sine. Okay, it's a hyperbolic from Calc 1. Okay. The nice thing about sinh and cosh, C-O-S-H, is that they are derivatives of each other. Derivative of sinh is cosh, derivative of cosh is sinh. I'll put that again. So sinh x prime is cosh x, and cosh x prime is sinh, not negative sinh, but just sinh. So they are derivatives of each other. All right, so I'm integrating from 0 to 2. Let u be y, dv is sinh y dy. So SINH, I'll pronounce it as sinh. It stands for hyperbolic sine, but that's too hard to say. I'll just say sinh. Okay, differentiate, du equals dy. There's that theme again. If u equals y, du equals dy. Integrate, v equals cos y. And one thing you may notice about the d stuff, this side, it starts off with no d's, but when you get over here, they both have d's. This side's the reverse. They start off with d's, but when you get over here, no more d. That will always happen. Okay, notice that's a theme for all the other ones I had. Okay, so again, here no d, but over here, d's. Here, both of them have d's, and here, no d's. All right, so by formula, it's uv, so y cos y. Okay, now here's a little technicality. Since this is a definite integral, when I take something out of the integral, I'm supposed to write this from 0 to 2, right? You know how you bring this over to the right-hand side and straighten it out? That's all. Okay, then minus integral from 0 to 2 of v du, so that's cos y dy. And then the next step, I just put it all together. So the integral of cos is sinh. Again, that's nice. You don't have to worry about signs, SIGNs. Okay, they are derivatives of each other. Okay, so this comes out to be sinh. So now I put it all together. Y cos y minus sinh y from 0 to 2. Okay, so I plug in 2 cos 2 minus sinh 2 minus, okay, if you plug in 0, that's 0. Sinh of 0 comes out to be 0 also. Hyperbolic sine of 0 is 0. It matches the sine function at 0 at least, so that's nothing. All right, so final answer is 2 cos 2 minus sinh 2. Okay. Okay, then 33, sorry I messed up here. By the way, what's all this stuff? I'm crossing all this out because this was from the 7th edition, then I realized none of these was in the 8th edition, so I'm crossing them out and doing this. So this should be 8th edition stuff now. All right, integral from 0 to pi over 3, sine x, natural log cosine x, dx. All right, so I noticed that the derivative of cosine is negative sine. I have that here except for the -1. That's not going to bother me. I just put the -1. Okay, so I'll do a regular substitution first. Now, you might say, why don't I let u be sine? If I let u be sine, the derivative is cosine, but I don't really have cosine. I have ln cosine. So that's not really going to work. So instead, let u be cosine. I'll have ln of u. And I already know how to integrate ln u. In fact, if I got to that stage, I can just go to this, in essence. Okay, so u equals cosine x. Okay, this is not integration by parts. This is just substitution, regular substitution. Du equals negative sine x dx. Okay, so I need a negative sign, SIGN, inside and outside. So -1 times -1. Because in order for me to substitute du, I must have a -1 sine x dx. -1 sine x dx. Okay, the 0 and the pi over 3 are for x. So I have to see what happens to u. So u equals cosine x. So I plug in 0. U is cosine of 0, which is 1. Plug in the upper limit pi over 3. Cosine of pi over 3, cosine of 60 degrees happens to be 1/2. Okay, so I'm integrating from 1 to 1/2, which is backwards. But again, that doesn't really bother me. So I have negative the integral from 1 to 1/2. Okay, so instead of ln cosine x, I have ln u. Much nicer. And then -1 times sine x dx. -1 sine x dx is du. And this is a common theme right over here. Okay, this is backwards, you might say. The smaller numbers here, the bigger number here. Sure, easy remedy. Change that to a positive. Turn these around. Right? That was a property from Calc 1. Okay, the integral from a to b is the opposite of the integral from b to a. So I turn these around, change that sign, and now it's perfect. Integral from 1/2 to 1 of ln u du. Okay, well, since I just derived the formula for that integral, I might as well just use it. All right, so the integral of ln x is this, x ln x minus x. So I'll put that down, except it's u, but you know, letters are just letters. So the integral of ln u is u ln u minus u from 1/2 to 1. Okay, plug in 1 ln 1 minus 1. Plug in a half, negative a half, ln 1/2. Sorry, I should have had minus a half here. Sorry, I messed up there. Minus a half. Okay, so let me see if I did this right. ln 1 is 0, so that goes away. Okay, I have negative 1 minus a half. That's negative 1 plus a half, which is negative a half. Okay, so negative a half minus a half ln 1/2. Sorry, that should be a negative 1/2 there. Negative a half. You could stop there, but I cleaned it up a little bit more. That negative a half, you can make it climb up as an exponent. You don't have to do that if you don't want to. And then the negative here means flip this, and the half means square root. Okay, so an acceptable answer is negative a half plus natural log of radical 2. Negative a half plus ln radical 2. But if you left it here, that's fine. Okay, then 37 is kind of different. Okay, you have to make a substitution first. Let me see if I can show it to you. 37. E to the radical x. First make a substitution and then use integration by parts to evaluate the integral. Integral is e to the radical x dx. If you can't see it, that's okay. I'll show it to you here. Integral of e to the radical x. Okay. What I'm going to do is let t squared be equal to x. I'll make that substitution. See, what do I want to do that for? Because then I'll be taking the integral of t, sorry, the square root of t squared, which is just going to be t. Right? So t squared equals x. Okay. Then if I differentiate, the left side becomes 2t dt equals dx. And by the way, t equals radical x. So let that be t. T equals radical x, therefore t squared equals x. So look at what happens if I substitute. The integral is now, I will stand for the original integral. So if you ever see me write I, that stands for the original integral. Later on, we're going to have I1, I2, all those things that are there. Okay, so integral of e to the substitute, radical t squared times dx. What is dx? 2t dt. Okay, so one more time, e to the radical x is e to the radical t squared. Then dx is 2t dt. So this changes to e to the t. Take the 2 outside. I now have 2 integral of t e to the t dt. And now I can integrate that by parts. So that was the tricky thing about this one. Okay, so leave the 2 alone. So this fits the category of polynomial times exponential. So if we ever have that, I'd put down let u be the polynomial, u equals t, dv is the rest, e to the t dt. Okay, differentiate, du equals dt, and just put the d's down. Integrate, v equals e to the t. All right, so the integral, there's a 2 out in front. So 2, all right, so by formula, it was u times v, t e to the t, minus the integral of v du. So VD was e to the t dt. All right, is this an easy integral? Sure is. I'm just integrating e to the t. So I started off with t e to the t. By using this formula, I'm just integrating e to the t. What's the integral of e to the t? E to the t. So I have 2, I distribute it, 2t e to the t minus 2 e to the t plus a constant. And the last step is to change t back. What was t? Radical x. So put radical x right there, and right there, and we're done. So 2 radical x e to the radical x minus 2 e to the radical x plus c. And there we go. All right, so I've done a lot of integration of parts. I want to show you a couple more that are much harder. I think I'll wait until after the break for that. Okay, so I think it's a good time to break right now. So what time do we got? About 8:05-ish or something like that. Okay, so let's break until about 8:15, please. Okay, so I'll stop the share. I'll pause the recording if I hit the right button. Share the screen. Okay. All right, I was going to do 2 more problems from 7.1, and then I'd be done with 7.1 essentially. Okay. I say only 2 problems. They're real bad problems. Okay, they're pretty long. Okay, that would be problems 17 and 19. There's just something weird about those. Okay, so I can show that to you quickly. So 17 has an exponential and a trig function. It's e to the 2 theta sine of 3 theta d theta. If you can't see it, don't worry, I'll do it in a second. Then 19 has z cubed e to the z dz. There's just something weird about these 2 problems, and I'll show you that. Okay, so I'll show you 17 and 19, and then I was going to be done with 7.1. So put these notes in code storage, don't study it. So we'll be done fairly early, and then what I thought I'd do as soon as I'm done is let you go back and ask questions from chapter 6. And you can keep asking questions up until 9:25, but if you finish early, I don't mind. Okay, so that means the game plan for now for Tuesday, right? So here we are. We've already finished that. And after I do those 2 problems, I'll be done with 7.1, I think. So Tuesday, I'll start lecturing on 7.2. I'll do 7.2, then I'll stop, let you ask questions, then we break, then we take the test. So if you want to give me a lot of questions tonight, you may. So think about what questions do I want to ask tonight, you might say, right? Because I'm almost done with what I need to lecture in 7.1. So when I'm finished, we can either take question and answers, or if nobody has anything, we can just leave early, okay? But, you know, I want you to have enough time to ask questions next time. Now, let's make next time the limit. Let's see, we have to stop before 8:25 on test days. So I'll lecture for a while, then you can ask questions up until 8:25. The reason why I say 8:25 is that gives us 10 minutes, 8:35, and then from 8:35 to our ending time of 9:25 is the 50 minutes that I've promised you. But I don't mind that you start earlier. So if questions and answer period stops earlier and we start earlier, you get more time, so be it. That's okay by me. And I'm guessing it's probably okay by you also, okay? All right, so I think I'll be completely done with lecturing 7.1 after I do, well, quote unquote, only 2 more problems, but those 2 problems are doozies, and I'll show you why. Okay, so here we go. So yeah, think of any questions you might want to ask from here. And yeah, let's make it where I don't take any questions on 7.1 because, you know, I'm not doing that until the next test, which is not for a while. Okay, so even though I'm lecturing in 7.1, just take notes if you want to and put it in code storage until, you know, much later. All right, so here we go. Okay, so 17, the original integral was e to the 2 theta sine of 3 theta d theta. Now, I gave you no rule if you had an exponential and a trig function. So if you look back in the notes, I had a polynomial and a trig function, let u be the polynomial. Or if I had a polynomial and an exponential, same thing, let u be the polynomial. What happens if I have an exponential and a trig? Turns out not really to matter, but let's just do this anyway. I'm calling the original integral I. There's a reason for that. So u equals e to the 2 theta, dv is the rest. Okay, u equals e to the 2 theta, dv is sine 3 theta d theta. So that means I do have u dv, which means I'm allowed to use the formula. Okay, and the way it works again is differentiate this side, integrate this side. So the derivative of e to the 2 theta is e to the 2 theta times 2. So du equals 2 e to the 2 theta. I forgot to put the d theta, sorry. Right, this side doesn't start off with any d's. Here, they're supposed to both have d's. This is the reverse, d and d, and by the time you get to here, no d. Okay, what's the integral of the sine? Integral of the sine is negative cosine, and then again by the chain rule, I multiply by 1/3. Okay, if I differentiate from Calc 1, if you took the derivative, when you got over here, you would say multiply by 3. Since we're not differentiating, but we're anti-differentiating, you do the opposite, divide by 3, or multiply by 1/3. So there's my v. Okay, so I is uv, so u times v, negative 1/3, e to the 2 theta, cosine 3 theta, minus the integral of v du. So now I have to put these two together. So for constants, I have a negative 1/3 times a 2. I'll bring that outside as a negative 2/3. E to the 2 theta, cosine 3 theta, d theta. And I have a double negative here. So I'm going to write negative 1/3 e to the 2 theta, cosine 3 theta, plus 2/3 e to the 2 theta, cosine 3 theta, d theta. Okay, and just a quick note, check that against the original. I started with this, exponential and sine. I now have exponential and cosine. Well, it didn't really get any better, but it didn't get any worse either. Okay, so I'm going to take a little time out and figure out I1 now. I'm calling this I1. So my convention is the original integral will always be I, and then within any integral problem, if I have to work on other integrals, I'll call them I1, I2, I3, and so on. Okay, so I1 is an integral within the problem that's different than the original. So I will always mean the original. Okay, so I'm going to take a time out and work on this I1. If I figure out this I1, I'll just put it back in here. You see, so it's like I'm taking a little time out and a separate subroutine, as it were, for you computer science people with that language. It's like you take a time out, figure that out, and then put it back in here. So I1 is this. So I'm doing a brand new problem. Okay, integral of e to the 2 theta, cosine 3 theta, d theta. If I figure out what that is, then I plug it into here. So I'm rewriting the original integral I. I'm now writing as negative 1/3 e to the 2 theta, cosine 3 theta, plus 2/3 of I1. Right? The original integral I, that stays the same, plus 2/3. Instead of writing all this stuff down, I'm just writing I1. So if I can figure out I1, I'll just put that over there. Okay, so now I'm going to work on I1, which is this. So I'll do the same stuff that I did before. Let u be e to the 2 theta. dv is the rest. Cosine 3 theta, d theta. All right, differentiate, integrate. du is 2 e to the 2 theta, d theta. v is integral of cosine, sine. And by the chain rule, same thing, times an extra 1/3. Should be a d theta there, sorry. Okay, put it together. I1 uv. That times that is 1/3 e to the 2 theta sine 3 theta minus integral of v du. So I have 2 times 1/3. That's a d theta there. So this is 2 e to the 2 theta d theta. Sorry about that. So 2 times 1/3 is 2/3. Integral of, so now what do I have? E to the 2 theta sine of 3 theta d theta, okay, which happens to be the same as my original I. E to 2 theta sine 3 theta d theta. Integral e to 2 theta sine 3 theta d theta. So certainly I'm not going to integrate by parts again. Seems like I'm just going in circles, okay? But actually we're not. We can keep going because this is the original I. I'm just going to replace this with the letter I. That's the reason why I'm calling it I. So I'm now going to say I1 equals 1/3 e to the 2 theta sine 3 theta minus 2/3 of that. And what is that? That's just my original I. There it is, e to the 2 theta sine 3 theta d theta. That was just what I started off with. That's the reason why I call it I. So I pick this whole thing up, plug it into here. Right? So I is negative 1/3 e to the 2 theta cosine 3 theta plus 2/3 I1. So in place of I1, I pick up this mess and throw it into there. So here we go. I is negative 1/3 e to the 2 theta cosine 3 theta, there it is, plus 2/3 I1. And I plug in all this stuff. 1/3 e to the 2 theta sine of 3 theta minus 2/3 of I. Okay, and now I just algebraically solve for I. There's an I here, there's an I here. Clean up the algebra and trig, and I solve for I. Okay, I know that's kind of weird. So distribute, that stays the same. That's 2/9 e to 2 theta sine 3 theta, and then 2/3 times a negative 2/3 I is minus 4/9 I. Okay. And remember, I is like 1I or 9/9 I. Add 4/9 I to both sides. So if I toss this over here, right? Normally, if you're trying to solve for I, put them together. So I have 9/9 I, 1I, plus 4/9 I, that's 13/9 I. So 13/9 I is blah, 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 blah. And then I just multiply both sides by 9/13. Okay, so 13/9 I is negative 1/3 e to the 2 theta cosine 3 theta plus 2/9 e to the 2 theta sine of 3 theta. Now just multiply both sides by 9/13 and you got it. So I have the original I. Okay, so 9/13 times that, 9 cancels 3, it'll be negative 3/13 e to the 2 theta cosine 3 theta. And then I multiply that by that, 9's cancel out, 2/13 e to the 2 theta sine of 3 theta. And then the last thing that students might forget, remember this is an indefinite integral. So even though it doesn't show up anywhere here, you now need to put plus c in the final answer. So finally, that's it. Okay, so that was a doozy of a problem. Okay, so I'll run through the logic one more time. So we had exponential sine, integrate by parts, exponential cosine. Okay, call that I1. Integrate by parts again. I'm back to exponential sine, same as the original. Okay, so no need to keep integrating by parts. Yeah, but don't panic. This is the same as I. So call it I, the variable I. When I plug in, I now can solve for I. I have an I on the left side. I have an I on the right side. Get them together and solve for I. And that's what you have here. Okay. All right, then I was going to show you 19, and now it's the last one. So yes, we are down to the last problem, quote unquote, but again, this is a long last problem, so it'll take a while to do this last one. And then I'm done. So after that, it's your choice. We can either have question and answer, or if that stops, we can leave and end. And that'll let you ask question and answers next time, Tuesday, before the test. But you know, if you want to get some stuff out of the way tonight, that'll be fine. Okay, so think ahead of time. Do I want to ask this question? Do I want to ask that question after I'm done with 19? Okay, z cubed e to the z dz. First thing I want you to notice, of course, is it doesn't matter what letter you pick. I mean, we like x. I guess they could have x cubed e to the x dx, you know, but you can have y cubed e to the y dy, or z cubed e to the z dz, or t cubed e to the t dt. They're all the same, right? All right, so this falls in the category of polynomial exponential, right? So I showed you a while back. If that happens, let u be the polynomial and the exponential be the rest. So u equals z cubed, dv equals e to the z dz. U dv. Differentiate, integrate. So du equals 3z squared dz. Integrate, that's easy. Integral of e to the z is e to the z. So v equals e to the z. Throw it in the formula. So I is u times v. So u times v is z cubed e to the z minus the integral of v du. So that times that, I'll take the 3 out, z squared e to the z dz. Okay. So before going on, let's see what happened. I started off with z cubed exponential. I now have z squared exponential. Did it get easier? Yes, it did. It went from z cubed to z squared. So I'm going to integrate by parts again. Can you guess what happens the next time I integrate by parts? Z squared is going to go down to z, e to the z. Then I do it one more time, and then finally there's no more z. Okay, so that's typically what happens in this situation. So I have to integrate by parts 3 times. Now, unlike this one, 17, where it never got better, this one does get better. It goes from z cubed e to z. Turns out every time you do this integration by parts, the exponent gets knocked down by 1. So it'll become z squared e to the z, and then z e to the z, and finally just e to the z. So that means, now I'm never going to give you anything this bad, but if you had, let's say, x to the 10th exponential, you could do it. So x to the 10th exponential, if you do it, then it'll become x to the 9th exponential. Do it again, x to the 8th exponential, then x to the 7th, 6, 5, 4, 3, 2, 1, and then finally it's gone. Then you just have exponential. You'd have to do it a whole bunch of times. Okay, so here you have to integrate by parts 3 times. First time 3 goes down to 2. Okay, so I'm going to call this I1. So I1 is the integral of z squared e to the z dz. So the original I is now z cubed e to the z minus 3I1. So keep that in code storage for when I substitute back. So now I'm going to integrate that. That looks like an integration by parts all by itself. Brand new problem. Okay, so I've got that. I take a timeout from the main program, so to speak, and I do this sub-program. Okay, I'll call another routine, as it were. So now I'm going to stop and figure out this, z squared e to the z integral. So I1, integral of z squared e to the z dz, do the same thing. So let u be the polynomial, u is z squared, dv is e to the z dz. Differentiate, integrate. du equals 2z dz, integrate, v equals e to the z. Throw it in the formula. I1 is uv, z squared e to the z, minus the integral of v du. So there's a 2, I'll put the 2 out, and then multiply the rest, z e to the z dz. So there it is, it happened again. The z squared e to the z became a z e to the z. So we do it one more time, finally it's down to just e to the z. Okay, so notice we started with z cubed e to the z, integrate by parts once, z squared e to the z. Do it a second time, z e to the z. So do it one more time, I'll just have e to the z, and I know how to integrate e to the z. Okay, so guess what I'm going to call this thing? I2. Okay, so I is the original integral. If I have to do integrations within integrations, I'll call them I1, I2, I3, however many I need for one particular problem. Okay, so I'm going to rewrite this as I1 is z squared, that's a 2 there, z squared e to the z minus 2 times I2. So I've got that in storage for I1. Now I'll take another timeout, figure out I2. See, once I figure out I2, I put it here. That gives me I1. Once I have I1, I go way back to here, and I get the original I. Okay. For you computer science people, this is almost like a recursive call. For you computer science people, you know about recursion, right? You just call something over and over and over again. So here you call something 3 times. If you have no idea what I'm talking about, don't worry about it. I just thought I'd give some application to you computer science people that this is sort of like recursion. But anyway, okay. So we have I2. All right, so now I2, I'm integrating z e to the z dz. So let u be the polynomial. U equals z, dv equals e to the z dz. Differentiate here, integrate here. This one again, just put d's. Put a d there, so du equals dz. Or you can say the derivative is 1 dz, so it's 1. And same thing, v equals e to the z. All right, so I got it. So I2 is uv z e to the z minus the integral of v du. E to the z du is dz. And there it is, just as we anticipated. Okay, z e to the z became just e to the z. So every time I integrate by parts using this technique, I drop the exponent by 1. Right? So z cubed e to the z. Integrate by parts once, z squared e to the z. Do it again, z e to the z. Do it again, just e to the z. And there we go. So the integral of e to the z is just e to the z. So this is my I2. Okay, so now I start back substituting, everything else. So this is the expression for I2. Now I go back here. And again, this has applications for you computer science people. You know how you figure something out and then go back to a previous call, and that gets substituted back, and that goes back to a previous call, and so on. So now I know I2 is this, right? So I plug that right back over here. So I1 is z squared e to the z minus 2I2. And I now know that I2 is this mess. So I put that in there, clean that up. So z squared e to the z minus 2z e to the z, and then negative 2 times negative that. So it's plus 2 e to the z. I think you probably caught this drift already, but I'll write my z's with a little mark in it. Okay, because the way I write my z's, if I write it like that too fast, you might think it's a 2, right? Okay, so my z's, I'm always going to put a little mark like that. I'm not saying you have to do that, but you know, if you want to get very exact. Sorry, to me, I'm too lazy to make it sharp like that. So I just kind of go quickly, and then you say, well, is that a z or a 2, right? So I'll put a little mark there to distinguish that. Anyway, that is now I1. So I1 calls all the way back to here. So I finally have I. So I is z cubed e to the z minus 3I1. So there we go. Z cubed e to the z minus 3I1. Here's I1, and then plus z. Okay, and now the rest is just some heavy-duty algebra. And what did I do here? I decided to factor out the e to the z. So I factor out the e to the z. I have z cubed minus 3z squared plus 6z, negative 3 times negative 2z is plus 6z, and then minus 6 e to the z plus c. So this, at long last, is the final answer. Okay, so that was quite a problem. Now, what am I doing over here? I was actually trying to show that the derivative of this thing actually is z cubed e to the z. I'll go ahead and show you that. Okay, you know the derivative of any constant is 0, right? Okay, so by the way, I'm almost done in about a minute, and then I'll open up the questions and answers in preparation for the test if you want. Okay, so product rule, right? First function, second function. So the derivative is the first times the derivative of the second. What's the derivative of e to the z? E to the z. So I copy that down. Plus the second, e to the z, times the derivative of the first. So what's the derivative of the first function? 3z squared minus 6z plus 6. Okay, so I have all this. There's a common factor of e to the z, and notice what happens. The negative 3z squared cancels the positive 3z squared. I have a plus 6z and a minus 6z, and I have a negative 6 and a positive 6. They all cancel out. I just have z cubed e to z. Now, what do you know? It does work. The derivative of my answer is this. And you probably noticed integration is way harder than differentiation, right? To go from here to here was quite a stretch. But to take the derivative of this was only, less than a minute maybe, right? It's very easy to show the derivative of this is this. But to integrate this was much, much more difficult. Is that right? Okay, so that's as much as I was going to do. And so, once again, I'm here. I'm actually done with 7.1. Okay, so next time I'll get started with 7.2. And then questions and answers, break, and then we take the test. Okay, all right, so I'll let you ask questions now. It's only 8:40 something, so we have plenty of time. Or if you want to end early, we could do that too. So let me stop the share for a moment. Let me check the chat. Okay. And if I miss your question in the chat, put it in the chat again. Or if you want to unmute yourself and say something. Okay, so bear with me as I check back the chat. Again, if you're not sure about attendance, just email me because I put it away and I don't want to mess with it anymore. Blah, 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 blah. Okay, calculators are okay on the test. Tests are worth 100. Show all your work. Let's see. Okay. All right. So question about 6.3, number 5. Okay. So let me get the book here. I'm still recording, by the way, so you can check this later. 6.3, number 5. Okay, so let me write the problem down and then share the screen again. And you can keep putting stuff in the chat if you wish, for as long or as short as you want. Okay, so back to sharing the screen. Sorry, this always takes a moment. Okay, 6.3, number 5. Using the shell method, y equals e to the negative x squared, y equals 0, x equals 0. So that's the x and y axes. X equals 1. And it says you're spinning it about the y-axis. Okay. So you don't need an accurate graph. Plug in 0, you get 1. Plug in 1, you get e to the negative 1. That's 1 over e. That's lower. So we're going like that. To use the shell method means you slice delta x. Okay, if I take this piece and spin it about the y-axis, you see shells. That's not true if I did slices delta y. Delta y, I would have disks. Imagine if I sliced like that, okay, then you see disks. Okay, so the height is y, radius is x. So integrate from 0 to 1, 2 pi x y is e to the negative x squared, dx. Okay. That's an x squared there. The 2 came out kind of funny. All right, so this is a substitution. U equals negative x squared. Du is negative 2x dx. Okay, we know the 2 pi is going to come out. All right, that's going to be u. I have x dx. I need negative 2x dx before I can substitute. So I just put a negative 2 inside and a negative 1/2 outside. So outside I have a negative 1/2 times 2 pi, and I change the limits. Okay, so when x is 0, u equals something, and when x equals the upper limit of 1, u equals something. So I plug in. When I plug in 0, I get 0. If I plug in 1, I get -1. So I'm integrating from 0 to -1 of e to the negative x squared. That's now e to the u. This thing here becomes u. And whoops. And all of this becomes du. -2x dx. -2x dx du. Okay, and cancel, cancel. The usual trick, you say -1 belongs in the bottom. Yeah, just switch it and change the sign. That's perfect. You get rid of the negative, and the smaller number will become here, and the top number becomes here. Okay, that's a recurring theme that happens a lot. So instead of -pi, I have +pi, and now I'm integrating with -1 on the bottom and 0 on the top. So from -1 to 0 of e to the u du. Okay. So that's pi. Integral of e to the u is e to the u. -1 to 0. Take the pi out. Plug in 0, you get e to the 0. That's 1. Plug in -1, you have e to the -1. And you can just leave it like that. Okay. So there really wasn't a chain rule there. Yes, Tiale, did you want to say something? Or
Yeah, I don't really get the x equals 0 and then u equals 0 part. Could you explain that one more time, please?
okay. So the original integral was going from 0 to 1. Okay, that's for x. But I'm switching everything over to u. Okay, I can't leave it 0 to 1 because 0 to 1 are the limits for x. But I'm changing the whole problem into u. So I'm not going to have x anymore. I'll have u. Dx is going to become du. And these numbers that were originally x, I have to find out the corresponding u values. So the whole problem is going to be in u. I'm burning the bridge, so to speak. I'm not going back to x anymore. I'm just doing everything in u. Okay. In order to do that, I figure out what happens when x is 0 and what happens when x is 1. So I plug in x is 0. Put a 0 right here. You get -0 squared. That's still 0, right? And then if I plug in 1 for x, I get -1 squared, which is -1. Remember, it means 1 squared, and then put the negative onto that. Okay. So it's not really a chain root. This is not a chain root instance, if that's what you're worried about. That's what I have here. I don't know if that answered your question, Tiali, but I can show you some other chain root situation if you want. Maybe I'll just show it anyway. Meantime, if anybody else has a question, you can ask. But again, integrating with the chain root backwards for constants, right? So I don't know. What is the derivative from Calc 1 of e to the 7x? So what's the derivative of e to the 7x? E to the 7x times 7. Chain root, right? You leave it alone, e to the 7x. Then the chain root says I have to differentiate by, take the derivative of 7x. Derivative of 7x is 7. By the way, this only works for constants. Okay, if you have a constant thing to multiply by, it doesn't work for variables. Okay, we'll see that later. Okay, so therefore, what's the integral of e to the 7x dx? Well, you know, integration and differentiation are opposite operations. So if I differentiate, I multiply by 7, right? So if I integrate, I divide by 7, which means multiply by 1/7 usually. Okay, so that's how the chain root works here. I'm not sure if that answers your question, but that's the best I can think of right now.
So for question 5, why did we have to do u substitution?
Why do we have to do u substitution? Because number one, we don't like integrating e to the negative x squared, right? I don't like something that complicated. I want something as nice as just u. Okay? And then the second thing that tells me to do a u substitution is because the derivative of that exponent appears elsewhere in the problem. The derivative of negative x squared is elsewhere x, except for a constant. I didn't have the -2, but you can always put a constant inside and outside. Okay, so the derivative of negative x squared is x, almost, except for a negative 2. Okay, so you can put in a negative 2 and outside put negative a half. You can do that only for constants. You're not allowed to do that for variable expressions. Okay, so if I see a function like that and the derivative is elsewhere except for a constant, then I would do a U substitution. Okay? In that sense, it's sort of like the chain rule on the differentiation sense, not really in the integration sense, but that's how you would do this kind of substitution. So why do I substitute? I didn't like that, so I call it U. And furthermore, the derivative of negative x squared showed up elsewhere in the problem. In other words, x. Okay. I don't have the negative 2, but that's easy. I can put the negative 2 in and negative a half outside. Okay. All right, let's see. 6.4, number 9 is asked for. Let's take a look at that. If anybody else wants to jump in with questions, you may. Okay. 6.4, number 9. You have 2 joules of work. To stretch a spring from its natural length of 30 centimeters to a length of 42 centimeters. Okay. Okay, I have to do it in meters, so that's 0.3 meters, and this is 0.42 meters. Okay, so I'm using Hooke's law. F is equal to kx, and we know we're integrating the force. All right, how much work is needed to stretch the spring from 35 centimeters to 40 centimeters? First, I have to find out the k. All right, so now F equals kx. It's based on natural position, so it's already at the natural position. So we're really going from 0 to 0.12. Because we're not taking the distance away from the wall. Okay, 0 is considered the home position, the natural position. Okay, so I'm going from 0 to 0.12. So the integral from 0 to 0.12 of F, which is kx, dx. You integrate the force. Right? That was also like problem 3. That part's similar to problem 3. Okay, so that's kx squared over 2 from 0 to 0.12. Plug in 0, you get 0, so you get k 0.12 squared over 2. So that's the work, and they told us that it was 2 joules. Okay, so I multiply by the reciprocal. So it's 2 times 2 over 0.12 squared. Okay, multiply both sides by 2 over 0.12 squared. Okay, I believe it was 277.7 repeating. So F is 277.7 repeating x. So that's now the force function. Okay, so part A says what? Hey, you're now going from 35 centimeters to 40 centimeters. Okay, so the natural position was 30. Okay, that's the real 0. So here you're really going, so remember 30 centimeters is the natural position or the home position. So if I'm going from 35 to 40, I'm really going from 5 centimeters away from home to 10 centimeters away from home position. And that comes out to be 0.05 meters to 0.10 meters. So that's how I integrate. So the work is the integral from 0.05 to 0.10 of 277.7 repeating x dx. etc. Okay, your answer is going to be so many joules. Okay. So, that's going to be what? X squared over 2, plug in 0.10, plug in 0.05, and get what you need. And then part B, where'd it go? How far beyond its natural length with a force of 30 newtons keep the spring stretched? Okay, so part B, had to do F equals KX. So the force they gave me was 30 newtons, was it? Yeah. 277.7 repeating X. Divide both sides by 277.7 and you got it. So X is 30 over 277.7. Now, I think that comes out to be 0.108 meters, if I'm not mistaken. But whatever it was, you have to give the answer as centimeters because that's how the original problem was. So even though when you're working the problem out, the metric understanding is that you're doing meters and newtons and kilograms and so on. But since the original problem had everything in centimeters, you should give the answer back as centimeters. I think it was 10.8. Do I want to spend the time to figure it out? Okay. 30 divided by 277 points. Yeah, 10.8. Okay, let me see. I don't see anything else in the chat right now, so I'll stop the share. Let's see, nothing else in the chat for now. Okay. Okay, 6.5, number 11. Okay, let's see what that is. What time is it? 9 o'clock. Sometimes I forget what time it is. So if I end up going past the time, somebody holler and scream at me. Okay. 6.5, 11. Okay. So, get my paper for that. After every problem I do now is one more that you can review, right? Okay. F of x equals 2 sine x minus sine 2x between 0 and pi. And yeah, don't worry about the sketch. Okay, so we're not sketching that. 2 sine x minus sine 2x. Okay. So go back to sharing the screen. All right, so the average value is 1 over b minus a. Pi minus 0 is just pi. Integral from 0 to pi of this stuff, 2 sine x minus sine 2x dx. 1 over pi. Okay, integral of 2 sine x, negative 2 cosine x. Okay, here's chain rule again. So what's the integral of negative sine, positive cosine, leave a space, and now by the chain rule, okay, if I ask for the derivative, you would multiply by 2. Since I'm integrating, I divide by 2 or multiply by 1/2. Okay, so 1 over pi, paren, minus paren. Careful, this time when you plug in 0, you might not get 0. In fact, I'm pretty sure you don't. Okay, let's see. What's the cosine of pi on my unit circle? 180 degrees. I want the x coordinate here. X coordinate is negative 1. So negative 2 times cosine of pi. I'll write it. Plus 1/2 cosine of 2 pi. Minus plug in 0. Negative 2 cosine of 0. Plus 1/2 cosine of 0. Cosine of 0 is 1. So 1 over pi. So cosine of pi we said was -1. That's -1. So -2 times -1 is 2. Cosine of 2 pi, that's the same as the cosine of 0, which is 1. So 2 plus a half minus cosine of 0 is 1. So -2 plus 1/2. So clean that up. 1 over pi. 2 plus 1/2 plus 2 minus a half. Looks like the halves cancel out. So I have 4 over pi. 4 over pi looks like. Okay, Tiali, you're welcome. Okay, and let's see. 6.2, 27, 29. Let's see. Okay. Point 227, region 3 about OA. Region 3 about OA. Region 3 is the middle one. OA is the x-axis. Okay, so let me try to show that to you. Spinning it this way. This is y equals x. Y equals the 4th root of x. Okay, so I'll slice delta x just because I'm more comfortable with that. So it looks like the washer method. Okay, so I have a bigger radius and a smaller radius. So it's pi big R squared minus pi little r squared is what I'm going to integrate. Okay, so the volume is the integral from 0 to 1. Pi bigger radius is the 4th root of x, which we're going to write as x to the 1/4 squared minus pi, the lower function, which is x squared dx. Take out the pi. X to the 1/4 squared is x to the half. X to the 1/2 minus x squared dx. The integral of x to the 1/2 is x to the 3/2 divided by 3/2 minus x cubed over 3, 0 to 1. Paren, 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 paren. Plug in 0, you get 0. 0 minus 0. Plug in 1, you have 2/3 minus 1/3, which is 1/3 pi, or pi over 3. It looks like it's pi over 3. Okay, 29 is same region, but about AB. AB is the line x equals 1. Okay, so 29 so about AB, we're going here. X equals 1. Y equals x. Y equals 4th root of x, like that. Okay, now since this section was specifically on the disk method or washer method, I'm going to do it by that. And that means I have to slice delta y this way. Okay, so since I'm integrating with respect to y, I want x as a function of y. So x is equal to y to the 4th. If I raise both sides to the 4th power, x equals y to the 4th. Okay, so this is my bigger radius, and this is my smaller radius, little r. So I have to figure out what those are. Okay, so for little r, from here to here is 1. From here to here is x. So this is 1 minus x, which is the same as 1 minus y, since I'm integrating with respect to y. And then the distance from here to here, big R, this is 1. Again, this is x. So this is also 1 minus x, but it's a different x. 1 minus y to the 4th. Okay, so the volume is integral from 0 to 1 of pi big R squared minus pi little r squared dy, and then I'll just say etc. Let's see. Yeah, sorry, I guess I forgot part B, Lucas. 6.5, 11B. So let's see, we had F average was 4 over pi. Find C such that F average equals F of C. So that means 4 over pi equals 2 sine x minus sine 2x. Oh, okay, I see what you mean. That can't be done very easily. So yeah, we'll have to skip that. Skip 11B, as it turns out. Sorry about that, Lucas, and everyone else. It might actually be possible, but it's more convoluted. It's because you have a double angle. That double angle kind of fouls things up. Okay, so yeah, just skip it. Okay, what time is it now? 9:10, 15 more minutes at the most. Okay, let's see, have I caught up with the chat? No. I think I've caught up with the chat. Unless if I miss you, you can put it in the chat again or unmute yourselves. Okay, so I'll come back. All right, anybody else, please? No more? Okay, I don't think I have anything else here. Let me go back. Okay, I guess we can stop, folks. All right, so quick reminder, we'll stop. Homework is due Tuesday, test Tuesday, but I will get started on the next section. So 7.2, I'll lecture a while. Questions and answers. If you don't have questions and answers, we can start the test faster. Okay, the limit for ending the first half will be 8:25, so 10 minutes would be 8:35. That gives you 50 minutes. But if we want to stop questions and answers earlier and start the test earlier, that'll be fine too. Okay, so I think what I'll do again is I'll project the test questions on my overhead here, but during the break, I'll send it via Canvas or email so you can get it there in case you want to print it out also. Okay, all right, I think that'll do it for tonight, folks. So we'll end early and that'll do it. All right, so good night, everybody. Have a good weekend and see everybody on Tuesday. All right,
Bye,
good night,
Mr.
everyone.
Long.
Thank you.
Good night.
Bye.